Hello friends, welcome back to my channel. Today I'll be talking about molecular diffusion in multi-component gas mixtures. I have done few videos on molecular diffusion in fluids where I have discussed molecular diffusion in a binary gas mixture. So in continuation with that, today I'm going to discuss molecular diffusion in multi-component gas mixtures. What is a multi-component gas mixture? It is that mixture which is having more than two gaseous components in it. So how to deal with molecular diffusion in such multi-component gas mixtures? That is what I am going to discuss today. Okay, so now let us understand the diffusion process. Molecular diffusion in gas mixtures. Multi-component gas mixtures. What are this? These are gas mixtures that contain more than two gaseous components in it. 3, 4, 5, so on and so forth. So mixtures containing more than two gaseous components. These are we are going to deal with such multi-component gas mixtures. Binary gas mixture where there are only two components, that is also a multi-component because it is containing more than one component in it. But when you have two components, the situation is a little bit simple. But when there are more than two components in it, complications get added. Okay, so we are going to deal with multi-component gas mixtures that are containing more than two gaseous components. The first thing that you have to note or you have to understand, what is the case? What is the fact? The fact is molecular diffusion in these mixtures is a complicated phenomenon. It is not easy to understand. It is not easy to describe mathematically. Mathematical equations that you can have for such situations, those equations are complicated. Okay, so in general, we are saying molecular diffusion in these gas mixtures, in these gas mixtures. Which mixtures? Which gas mixtures? Multi-component gas mixtures. Those mixtures which are having more than two gaseous components in it. Why the phenomenon is complicated? Let us understand. First thing is all of the components that are present in the gas mixture, they are diffusing. They are diffusing. They will be diffusing in all three directions. So this is one thing. The other thing is due to this, diffusion of individual components is getting affected by the presence of other components in the mixture. If a single component is diffusing, but due to presence of other components in the gas mixture, diffusion of that component is going to get affected. Okay, so diffusion of individual component is affected by presence of others. Since every component is diffusing, every component will have the diffusion coefficient. Every component will have its diffusion coefficient. Or you can say, to be more, you can say correct, every component is going to have a diffusion coefficient in every other component. I'll discuss one example which may help you understand what I have written over here. Every component has a diffusion coefficient in every other component. This is the fact. Okay? A highly complex set of mathematical equations is needed to describe the phenomenon mathematically. So when you have such complications, we will need complex mathematical equations to describe the process mathematically. Okay. So for example, let us consider a simple case. I'm calling it as simple even though there are four components in it. Which four components? We are considering a gaseous mixture that is containing A, B, C and D in it. Just four components. Why I'm saying just four components? Because there may be situations where there are 5 components, 6 components, 10 components in the gas mixture. So even for a mixture that is containing 4 components in it, you have quite complicated situation. Okay, so all the four components, they will be diffusing. A, B, C and D all will diffuse, and they will affect diffusion of others. So if A is diffusing, it will affect diffusion of B, it will affect diffusion of C, it will affect diffusion of D. Similarly, B will affect diffusion of other three components. Okay, so A will be diffusing in B, A will diffuse in C, A will diffuse in D. Same is the case with B. B will diffuse in A, B will diffuse in C, B will diffuse in D. So due to this fact, every component will have a diffusion coefficient in every other component. Every component will have a diffusion coefficient for its diffusion in every other component. So for example, for component A, there will be diffusion coefficient in B, diffusion coefficient in C, diffusion coefficient in D. For component B again, there will be diffusion coefficient in A, diffusion coefficient in C, and diffusion coefficient in D. Similarly, for component C, there will be diffusion coefficient in A, diffusion coefficient in B, diffusion coefficient in D. Similarly, component D will also have three diffusion coefficients because it will be diffusing in the other components as well. Okay, so uh, even for the case of four components, you have quite complicated case, and we will need to have or we require a highly complex set of mathematical equations to understand the process mathematically, understand the diffusion process mathematically. Now we will learn how to deal with such situations. How can we handle molecular diffusion in multi-component gas mixtures? Let us understand. Okay, so let us see how to deal with molecular diffusion in multi-component gas mixtures. Okay, what we can do or what we will be doing, we will be using effective diffusion coefficient, use of an effective diffusion coefficient. So you can deal with molecular diffusion in multi-component gas mixtures by using an effective diffusion coefficient. Now what is this effective diffusion coefficient? Let us understand. For a component in the mixture, how to define or what is an effective diffusion coefficient? For a component in a mixture, for a component in a multi-component gas mixture, an effective diffusion coefficient in the mixture is used instead of its binary diffusion coefficient in every other components. So instead of considering diffusion coefficient of a component in every other component, you can use an effective diffusion coefficient. So for example, in our previous example, we had four diffusion coefficients. For component A, you had DAB, DAC, and DAT. So instead of using each of this diffusion coefficient, you can go for an effective diffusion coefficient. You can use an effective diffusion coefficient and then calculate the other things. So in place of binary diffusion coefficients, you can use an effective diffusion coefficient. So for how it is given, let us understand. Let us understand it for component A. For component A in a mixture of n other components. So let us say that you have a gas mixture which has n components in it, and A is one of the component. So for such case, for component A present in a mixture of n components, how do you write an equation for the effective diffusion coefficient? The effective diffusion coefficient, we will be denoting it as DAM, diffusion coefficient of A in the mixture, DAM, diffusion coefficient of A in the mixture. So this is equal to Na minus Ya summation of Ni, where I is going from 1 to n, this entire term divided by summation of 1 upon dAi into Yi into Na minus Ya into Ni, where I is again going from 1 to n. Okay, so this is an equation which will give an effective diffusion coefficient for A in the mixture. Likewise, you'll have diffusion coefficient, effective diffusion coefficient for every other component. So for A, how it is given? It is given as DAM is equal to NA minus YA into summation of Ni, where I is going from 1 to n. So this is sum of molar fluxes of all the components divided by summation as I goes from 1 to n, 1 upon DAI into bracket yi into Na minus Ya into Ni. Okay, so this is an equation for effective diffusion coefficient of A in the mixture. So what are the terms involved in the equation? DAM is effective diffusion coefficient of A in the mixture. DAI, what is this? This is diffusion coefficient of component A in the ith component, where I will be going from 1 to n, and it will not include A in it. So if there are 4 components, I will stand for B, C and D. Are you understanding it? So here we have used binary diffusion. This is binary diffusion coefficient. Diffusion coefficient of A in ith component. Binary diffusion coefficient. DAI is binary diffusion coefficient of A in the ith component. YA is the mole fraction of component A in the mixture. You know what is mole fraction. So mole fraction of A in the mixture we are going to denote by Ya. Then Yi, you can easily tell this is mole fraction of ith component other than A. Then Na is molar flux of A, and Ni is molar flux of ith component. So this is N type of molar flux. So in my previous videos on molecular diffusion in fluids, I have discussed N type and what is N type molar flux, what is J type molar flux. So please refer to that video and you understand the concept. Okay, so the point is, on this slide we have written an equation for effective diffusion coefficient. We have written equation for effective diffusion coefficient of component A in the mixture. Okay, so this is the way in which you can deal with molecular diffusion in multi-component gas mixture. Instead of using binary diffusion coefficients, we will be using an effective diffusion coefficient. Okay, now if you look at this equation, the equation itself is a little bit complicated. So next we will try to simplify it. We will try to change it into a form that will be useful for us for actual use of that equation. Okay, so next we will discuss how we can simplify this equation so that it is usable. Okay, now let us understand how to use uh, the equation for effective diffusion coefficient. So in our previous slide we had this equation. It looks the equation looks complicated. Let us try to simplify it. Now equation this in what does this equation indicates? DAM, if you look at the equation, if you follow the equation, you will come to know that DAM, the effective diffusion coefficient, it is considerably changing with the diffusion path. It is going to change with diffusion path. So this equation indicates that as along the diffusion path, it is going to change. The equation indicates DAM is going to vary considerably with diffusion path. This is the case. This happens when you have this equation. But even though it is changing, what you can do for practical purposes, why its actual use, what you can do, you can assume a linear variation. It is changing, no doubt. It is changing from one end of the diffusion path to the other end. It is changing. But how can you simplify this? You can simplify it by assuming a linear variation. So we will assume that it is going to change linearly. The change will be along a straight line. We don't know what is the actual change, whether it is along a curve or anything else. So instead of going to what exactly the case is, you can assume this thing. You can assume a linear variation for practical purposes. This is one thing. Okay. Then the most common situation, in most common situation, only one component is diffusing. This is the most common situation. Or you can assume, say, out of all the components, only one component is diffusing. Most common situation is, or most common, or you can say most simple situation that you can consider. The most simple situation is only component A is diffusing. All other components, all other n minus 1 components, out of n, only A is diffusing, and all other n minus 1 components, they are not diffusing. This will be the most simple situation, and for this simple situation, diffusion of other components, that means how you are making the situation simple. You are making it by saying that other components are not diffusing, or you are neglecting diffusion of other components. We are saying only component A is diffusing. Most simple situation. So if this is the case, that means all n's in this equation, for n components there will be na, nb, nc, nd, so on and so forth. So all of those n's except na, they will be 0. nb will be 0, nc will be 0, nd will be 0, na will be 0, so on and so forth. There will be only one n that will have value, and that is na. When this is possible? This is possible when you say that only component A is diffusing. All other components are not diffusing. Okay, so for that case, all n's except na are 0. All other n are 0. All other n's are 0. Only na will have a value. Okay, so for this case, if you assume this, if you consider this common situation, this equation will get simplified. It will get simplified to this form. DAM is equal to 1 upon summation I, summation as I goes from B to N, yi dash upon DAI. Again, summation is taken over the remaining components other than component A. So DAM is equal to 1 upon summation of yi dash upon dai as I goes from B to N. So a quite complicated, relatively complicated situation. By making this assumptions for practical purposes. What is the first assumption? There is a linear variation, that is effective diffusion coefficient varies linearly with diffusion path. This is one thing, and the other thing is all other components, they are stagnant, they are not diffusing. Only component A is diffusing. That means all n's except na are 0. So if you have these two assumptions in your pocket, then this complicated equation takes a simple form. And what is that simple form? DAM is equal to 1 upon summation yi dash upon dai as I goes from B to N. So here, what is I dash? Yi dash? Yi dash is the mole fraction of ith component on a free basis. Mole fraction of ith component on a free basis. While calculate, I'm going to explain this, how to get this yi dash. So yi dash, for time being, you understand this is mole fraction of ith component on a free basis. While calculating mole fraction for ith component, A is not considered. That's why we are saying it as the mole fraction of ith component on a free basis. So let us understand. Let us understand this with a simple example. For that, what we will do, consider a gaseous mixture of three components. Now we will consider only three components, A, B, and C. So the effective diffusion coefficient of A in this case, in this mixture of three components, it will be calculated as 1 upon yb dash divided by dab plus y dash c divided by dac. So the previous equation, which was dam is equal to 1 upon summation as I goes from b to n yi dash upon dai. For the case of three components, the equation takes this form. DAM is equal to 1 upon y dash b divided by DAB plus y dash c divided by DAC. So this is diffusion coefficient of A in B, binary diffusion coefficient. This is a diffusion coefficient of A in C, binary diffusion coefficient of A in C. Now let us understand how to get this y dash b and y dash c. Y dash b, this is mole fraction of B on AA free basis, and y dash c, this is mole fraction of C on a free basis. How to get this? Let us understand. DAB, okay, this is let me tell you first. DAB is diffusion coefficient of A in B. DAC is diffusion coefficient of A in C. This is very much clear to you. Now let us understand how to get YB dash and YC dash. So YB dash is understood in this way. This is mole fraction of B, moles of B divided by total moles. But while calculating total moles, you see A is absent, Na is absent in that. That means there is this is free of A. That's why we are calling that as mole fraction of B on A free basis. So this is moles of B divided by moles of B plus moles of C. Total moles excluding moles of A. So you have mole fraction of B on A free basis. Similarly, you have mole fraction of C on A free basis, that is y dash C. This is moles of C. You please read it as moles of C. This is NC, moles of C. Moles of C divided by moles of B plus moles of C. Moles of C divided by total moles. Mole fraction of C on a free basis. So in this way, you have to get the values for y dash b and y dash c. In general, you can get uh, the value for y dash I, which is mole fraction of ith component on a free basis. Okay. Now next, having understood how to get effective diffusion coefficient in a simple situation, why I'm saying simple situation, we have assumed variation of DAM to be linear along the diffusion path, and second simplification is we are saying that all components other than component A, they are not diffusing, they are stagnant. Okay, so once you know how to calculate DAM, that is effective diffusion coefficient for A, now let us understand how to use that to get the rate of diffusion. So on this slide, we will understand how to calculate the rate of diffusion. So the case is only one component is diffusing and all other components are stagnant. So if that is the case, then the diffusing component exerts its partial pressure and all non-diffusing components exerts exert a combined partial pressure. So you have partial pressure of the diffusing component and combined partial pressure of all non-diffusing components. So for example, if you have a gas mixture of three components, which three components? A, B and C. A is diffusing and the combination, that is mixture of B and C, it is not diffusing or stagnant, then this case is equivalent to one gas diffusing in non-diffusing second gas. So in this case, the diffusing component, one gaseous component is diffusing, whereas the remaining gaseous components are stagnant. So in my discussion on diffusion in binary gas mixtures, I have discussed this case. You please refer to that video. Description, a link is given in the description section. Okay, so for that case, we know the rate of diffusion coefficient is given or can be given by this equation. So this is Na is equal to dAm. Now in place of dAb, which was true for the case of binary mixture, here dAb is replaced with dAm. Na is equal to dAm into P divided by RTZ into PBCM. I'll tell you what is PBCM. But those of you who have seen my video, this is in over here you had PBM. Now PBM is replaced with PBCM. You please check the video. So Na is equal to DAM P upon RTZ into PBCM into PA1 minus PA2, where PBCM is PBC2 minus PBC1 divided by ln of PBC2 divided by PBC1. It is basically logarithmic average of PBC2 and PBC1. In this equation, P is total pressure, R is gas constant, T is temperature, Z is length of the diffusion path, PA1 is partial pressure of A, the diffusing component at one end of the diffusion path, and PA2 is its partial pressure at the other end of the diffusion path. In the equation for PBCM, which happens to be the logarithmic average of PBC2 and PBC1, how to get PBC2? This is P minus PA2, total pressure minus partial pressure of A at end 2, whereas PBC1 is P minus PA1, total pressure minus partial pressure of A at the other end. Okay, so you have the two values, you take the logarithmic average and you use that logarithmic average in this equation to get the rate of diffusion. And you already know how to get DAM. So DAM is 1 upon Y dash B upon DAB plus Y dash C upon DAC. So in this way, you can find out rate of diffusion for a component that is diffusing in a multi-component gas mixture where only one component is diffusing, whereas all other components are stagnant. So with this, I end my discussion for this particular video. Here, I have told you how to calculate the rate of diffusion in a multi-component gas mixture, where a simple situation is considered. Okay. In my next video, I'll be solving one numerical. I will be discussing one numerical based on this. You please follow me on my YouTube channel. Please subscribe to my channel. Please hit the like button, and if you you also hit the bell icon so that you can get notified as soon as I upload a new video on my YouTube channel. Tell your friends to subscribe to my channel. We will have more such videos on various aspects of chemical engineering. For time being, thank you for being with me.